All right, so integration by parts is essentially the product rule in reverse. So the product rule from derivatives. So the formula that we're going to make use of here is, I'll write down, whoops. So essentially the formula we're using is as follows. This is uv minus the integral of v du. This is the integral of u dv. So I can kind of show you where this comes from if you want, but this is the main thing that we're going to be using. And this is when we have a product of two different types of functions that we're trying to integrate, and substitution doesn't work. So what did the product rule originally say so let's recall the product rule from derivatives. So that said, if you have the derivative of two types of functions, u multiplied with v, then the product is u prime v plus uv prime. So the idea here is essentially if you integrate both sides, right, if we would integrate both sides, and again, these are all u and v, these are actually functions with respect to, say, x or some input variable. But let's say we're just integrating both of these things, and for that reason, I don't have the differential. But right, integration should undo the process of the derivative here. So on this side, we just get uv, and on the other side, we can split it into two parts. On the one hand, we've got the integral of v with u prime, which instead of u prime, I'll call it du. And then the other one would be the integral of u with dv instead of v prime. So to get the formula above, basically, I can subtract the integral of v du. So I get uv minus the integral of v du, and this is equal to the integral of u dv. So that's why the formula essentially works. It comes right out of the product rule, just differentiating both sides. The main point is we've separated everything. So if you look at what we started with, we've got the integral of something complicated with the u and the v multiplied together. But now down here, we've worked things out as to where we've got, we're going to call one of our factors u and the other one dv. And we're going to be able to rewrite this integral in terms of two functions multiplied together and then a simpler integral, hopefully. So that's the idea. But essentially, we're just using the boxed-in things. We need to choose a u and choose a dv, and then we go from there. And again, it'll take a little bit of skill and practice learning which thing we want to pick to be the u, and which one we want to pick to be the dv. So let's jump right in and see how this works. So the first example here, we want to just compute the integral of 14x times e to the 2x dx. So the thing is, 14x is easy to differentiate, easy to integrate. E to the 2x, but the thing is, when you differentiate 14x, it would become 14, so it's simpler. Whereas e to the 2x, the integral and the derivative are fairly, they're not more complicated. You're just multiplying by a constant in either case. So in this example, the correct choice is going to be letting u be 14x and letting dv be this e to the 2x. And basically what you do is you differentiate the u, so you get du is equal to 14, and then I'll write dx as well. And then the integral of dv would be v, which is e to the 2x divided by 2. And now these are kind of like the constituent parts of the formula above, the uv minus the integral of v du. So this becomes your integral. So really what we do is we take u and we multiply it with v. That's the first part. So 14x gets multiplied with the e to the 2x over 2. and then we're subtracting the integral of v times du. So that's going to be 14 times e to the 2x over 2, and then we also have that dx. So notice that we didn't really use the dv in the formula for the integral other than to figure out what v was. So dv is not involved in the formula whatsoever. Okay, then we just have a little bit of cleanup to do. So 14x over 2 is the same thing as 7x. So I get 7x e to the 2x, and then minus, I'm going to be doing the integral of 7e to the 2x dx. And that integral, again, is just the straightforward e to the 2x over 2. It's the integration rule for the exponential function. So 7x e to the 2x minus 7 over 2 e to the 2x, and then plus a constant of integration, since this is just a general antiderivative. Okay, any questions there? Okay, so let's go ahead and work on another example. Again, you need to kind of see how all the different functions interact in order to see which choices are going to make sense. So I'll try and leave a few steps up from the previous one. So example, let's go ahead and compute. This one will be a definite integral. So we'll compute the integral from 1 to 2 of x to the 4th times the natural log of x times dx. Okay, so here we want to let u be the natural log of x. We haven't actually learned how to integrate the natural log of x. So that's one reason why we want to pick u to be the natural log of x. We do know its derivative, 1 over x, but we don't know its antiderivative yet. So that will mean v will be x to the 4th, or dv will be x to the 4th. So we pick u to be the natural log of x. We pick dv to be x to the 4th. So we differentiate u, so we get du is 1 over x dx. And we need to integrate dv, so the antiderivative of x to the 4th will be x to the 5th over 5. Okay, so these are all the parts we need to apply the integration by parts formula. So what do? We take u and we multiply it with v. So that's x to the 5th over 5 times the natural log of x minus the integral of v times du. So we've got the integral of x to the 5th over 5 times 1 over x dx. So that will simplify a bit. So x to the 5th over x is x to the 4th. So we have x to the 4th over 5 dx. And again, that has a fairly simple antiderivative of, oh, and remember, we're actually integrating. This is a definite integral. These are all going from 1 to 2, so it's going to happen at the end. So we've got this x to the 5th over 5 natural log of x minus x to the 5th over 25. And then again, we're plugging in 1 and 2 here. So let's see if we can do that. 2 to the 5th over 5 natural log of 2 minus 2 to the 5th over 25. And then we need to subtract when we plug in 1. So 1 to the 5th over 5, natural log of 1. Natural log of 1 is actually 0, so that's going to go away. Minus 1 to the 5th over 25. And that about does it. So 2 to the 5th should be 32. So we get 32 over 5 times the natural log of 2 minus 32 over 25. And then we're just going to have a plus 1 over 25. So we can write this, if we want, as 32 over 5 natural log of 2 minus 31 over 25. And let's go ahead and get a decimal approximation here. I've got about 3.196. And why don't we check that integral on Desmos to make sure that, just doubly confident that we got it correct. So I don't need to log in. I just want to go to graphing calculator. Okay, so this was the integral from 1 to 2 of x to the fourth times the natural log of x times dx. It always wants me to put everything in parentheses. I don't understand that part of this whole thing, but yeah, 3.196, same as what we got. So that's it for that example. Any questions so far? Okay. All right, so let's continue. Let's do one more, since I talked about natural log of x. We don't know how to integrate it. In fact, we now have the tools we need to integrate natural log of x. So let's just say compute each antiderivative, and we'll do a bunch. But yeah, I want to do natural log of x because it's actually interesting. We can use integration by parts to do it. So the first one, we have the natural log of x. Well, you might say, well, how do we use integration by parts because there's only one factor? Well, what you can do is you can think of the natural log of x as being multiplied by 1. So that's what we do here. And that will actually allow us to compute the integral. So we let u equal the natural log of x, and we let dv equal 1. So then du is 1 over x dx, and v is just x. And so when you do the integral, you get uv, which is x times the natural log of x, minus the integral of v times du, which is actually x times 1 over x dx. So you're actually getting x natural log of x minus the integral of 1 dx. And antiderivative of 1 would be x. So you get x natural log of x minus x plus a constant. So it comes up enough where it might be something you want to put in your memory banks, that the antiderivative of natural log of x is x natural log of x minus x. But as long as you remember that it's accomplished by integration by parts, then you're going to be okay. Let's actually check that. So how can we check it? We can actually take the derivative of x natural log of x minus x. So if you take the derivative, well, the derivative of the minus x is just going to turn into minus 1. But for the x times the natural log of x, you actually need to use the product rule there, right? So what would you get? Well, you'd have the first times the derivative of the second, so x times 1 over x, plus the derivative of the first times the second, that would be 1 times natural log of x, and then minus your 1 from before. So we end up with 1 plus the natural log of x minus 1, which is exactly the natural log of x. So it checks out from taking the derivative as well. So we now have the derivative of we now have the integral, the antiderivative of the natural log of x as well. B, let's go ahead and just, most of all of our product rules are going to basically involve either multiplying polynomials with logarithms or polynomials with exponential functions, since there's no trig in this class. So let's do the integral of x times e to the 2x. So again, when you have this set up, generally what you do is you let the polynomial part be u, and you let the exponential part be dv. So we want to let u be x, and we want to let dv be e to the 2x. So du is just dx here, and v is e to the 2x over 2. So then we can do our integral. So we get uv, which is just x e to the 2x over 2, minus the integral of v times du, which is just e to the 2x over 2 dx. And again, when you do the antiderivative there, you're basically just dividing by another factor of 2. So we get x e to the 2x over 2 minus e to the 2x over 4 plus a constant. Maybe we can do the part C right next to it. I think we have enough room. Let's do the integral from, let's try another polynomial. So let's use t squared times e to the t dt. So again, we've got a polynomial with an exponential. So what you want to do is you want to let u be your t squared and dv be the e to the t. So du will be 2t dt, and v will just be e to the t. And we can go ahead and rewrite our integral. So we're going to get uv, so that's t squared e to the t, minus the integral of v times du. So that's going to be 2t e to the t. And what do we have to do here? Well, it turns out that we just have to do the integration by parts again. But if you notice, well, yeah, so we just have to do it again, essentially. So basically do parts again. So if I'm going to do that one by parts again, I would let u be 2t, dv would be e to the t. So du is 2 dt, and v is e to the t still. So basically I'd have my t squared e to the t minus, then I've got my uv from here, so 2t e to the t minus the integral of v with du, which is just 2 e to the t dt. So we have t squared e to the t minus 2t e to the t. And then the antiderivative of 2e to the t is just 2e to the t. So the second, distributing the minus sign makes that a plus 2e to the t. And then I've also got my plus constant from integration. So had to do integration by parts twice on that one.
How did you decide to do the parts again?
Well,
what made you decide to do that?
How would you integrate 2t times e to the t otherwise?
Yeah, that wouldn't make sense.
So I mean, you'd have to see a substitution, which I don't see, because normally if there's a substitution, you might have something like t squared in the exponent. There's nothing like that, so substitution doesn't work. It's also not one of my basic formulas that I know. My basic formulas being just the polynomials, exponentials, logarithms. I know how to, basically take antiderivatives of all of those things, but it's a product of 2t times e to the t. So if you notice, everything we've done so far, with the exception of that natural log, we've kind of got two functions multiplied together, and substitution's not a viable option. So in this example, we had t squared times e to the t. Over here in part B, we had x times e to the 2x. That's not too far away from 2t times e to the t, right? You've got a polynomial times an exponential. So the next example we're going to have a polynomial times a logarithm. I just want to make sure that's not the one we did already. So like I said, a was just the regular natural log. This one yeah, so the one before was a polynomial times a logarithm. Again, that's two different kinds of functions multiplied together. So one of the reasons you have to use integration by parts. Okay, so that was C, right? So let's do part D. So the part D I have here is the integral from 1 to 2 of x squared natural log of x dx. So for this situation, when you have a polynomial and a logarithm, it's actually the reverse of what you choose to be u from when you have a polynomial and an exponential. So we're going to let u be the natural log of x and dv be x squared. So you might want to put that in your memory banks when you're choosing them. Usually if you have a polynomial times an exponential, the polynomial is u. But when you have a polynomial times a logarithm and you're doing integration by parts, you want to let the polynomial be dv. So here I'm going to pick u to be the natural log of x, and dv would be x squared. So, I mean, you can try it the other way, but the problem is what happens after you do the formula, it gets more complicated rather than less complicated. And so you'll just end up spinning your wheels for a really long time until you go back and try the other choice for u. So here we have du is 1 over x dx. And then here v would be x cubed over 3. So my integral, I've got u times v, so I've got x cubed over 3 times the natural log of x minus the integral of v times du. So that's x cubed over 3 times 1 over x dx. And again, all of this is from 1 to 2. I'm just going to write the limits at the very end. I mean, I can write them here for now, but we really have to plug everything in. So I'm just copying down the first term again, nothing new there. The second term, the integral, the x cubed over x is going to make that now an x squared over 3. And so the antiderivative there is going to become x to the third power over 9. We're going to add 1 to the exponent, and there's going to be another 3 in the denominator. So I've got x cubed over 3 natural log of x minus x cubed over 9, and then we're plugging in 1 and 2. So I'm going to get 2 to the third over 3 natural log of 2 minus 2 to the third over 9, then minus 1 to the third over 3 natural log of 1. Natural log of 1 is 0, so that term is going to vanish, minus 1 to the third over 9. So then we're going to get 8 over 3 natural log of 2. This term is going to become 0. Then you have 8/9 minus 1/9, so that's going to be, actually negative 8/9 plus 1/9, so it's going to be minus 7 over 9. So yeah, that should be the value. Again, we can check this one. I didn't do a decimal already, so I can check now. 8 times the natural log of 2 divided by 3 minus 7 over 9. About 1.0706 or something like that. So we can check and make sure we did it right on Desmos again. Back to the calculator. So very similar to this one. We had x squared, though. We were going from 1 to 2. Yeah, so we got it right. 1.0706. Okay, let me give you some examples to try and see how things are coming. I'll give you 2 to try. Then there's a trickier one we'll look at the end of class if we have the time. I have a harder example lined up. Okay, so example, say try at home. So A, we have the integral of 14x e to the 2x dx, and B, the integral of from, we already did that one. So I'll just make another one up. Let's just say x cubed, natural log of x or something, dx. So these should be very similar to ones we've already seen. So they shouldn't take you too long. So go ahead and write them down. I don't know. We don't have too many people. Do you want to break into two groups today, or are you okay working on your own? So let me know in chat if you want to do breakout sessions. I can set it up where we do 2 breakout sessions. So do we have a consensus? Individuals fine. All right. Okay. Yeah. Again, it should look pretty similar to ones we've done so far. So I'll just leave it up. I'll give you 5 minutes or so. Again, this should look very similar to the examples we've seen today. Okay, why don't we work through these two? Then we'll go through one more problem that I have that's pretty difficult. So for this one, again, in this situation, we want to let the polynomial part be u. So u is 14x, and then dv should be our e to the 2x. So then du becomes 14 dx, and v becomes e to the 2x over 2. So then we get uv, so 14x. This may have actually, this feels like the same problem that we had before, so this one may be a duplicate. Minus the integral of v times du, so it's going to be 14 times e to the 2x over 2 dx. And so we have 7x e to the 2x minus 7 e to the integral of 7 e to the 2x dx. And so we get our final answer there of 7x e to the 2x minus 7 over 2 e to the 2x plus a constant. So that's it for A. B, again, going to be pretty similar, but here the choice of u is going to be the opposite, right? Our polynomial part x cubed is going to be dv in this problem. So u is the natural log of x. dv is x cubed. So du is just 1 over x dx. And v is x to the 4th over 4. So we end up with u times v, so x to the 4th over 4 times the natural log of x minus the integral of v times du. So we've got x to the 4th over 4 times 1 over x dx. So we have x to the 4th over 4 natural log of x minus the integral of x to the 3rd over 4 dx, canceling that 1x out. And then the antiderivative there is going to be x to the 4th divided by another 4. So it's going to be 16 in the denominator of the second term. So we have x to the 4th over 4 natural log of x minus x to the 4th over 16 plus a constant of integration. So that's it for those two. So probably at this level, you're able to finish all the problems on the homework. I don't think there's many more difficult than that. Maybe I'm wrong. We'll have Friday to go over that, though. Anyhow, let's go over this one, which is one last example, a little bit trickier. So let's do the integral here from 0 to 1 of x cubed over the square root of 4 plus x squared. So this is an exercise from the textbook, actually. So the thing that makes this one so tricky is the substitution is kind of difficult. Like you might look at it and say, well, I probably want to pick u to be either x cubed or maybe 1 over the square root of 4 plus x squared or something like that. But this is the really tricky part to the problem. What the choice of u is here is x squared. So if u is x squared, that would mean dv would have to be x over the square root of 4 plus x squared. And this second dv can be integrated now because x over the square root of 4 plus x squared can be done via substitution. So let's go ahead and move forward. So du here is going to be 2x dx. And I'm going to tell you what v is. V comes out to just be 4 plus x squared to the 1/2. But we can do it over here on the side. So v is computed by a u substitution. So actually, we've already used u in this problem, so why don't we'll make it a w substitution. So let's say w is equal to 4 plus x squared. Then dw would be 2x dx. So dw over 2x is dx. So then you can go ahead and, change over your integral. So your integral would become the integral of x over the square root of 4 plus x squared dx becomes the integral of x over the square root of w times dw over 2x. Your x's cancel out, so really this is the integral of 1/2 times w to the negative 1/2 power. That is what the square root is, the 1/2 power, and because it's in the denominator, that's why it's w to the negative 1/2. So then integrating this, we would have add 1 to the power would be 1/2. Dividing by 1/2 would be the same as multiplying by 2. So we get 2 times 1/2, w to the 1/2, and that's just w to the 1/2, or as we said for v, 4 plus x squared to the 1/2 power. So the substitution is really sneaky, and the substitution, or the choice for u and dv is sneaky, and that's so we can actually compute dv by this u substitution. So anyway, back to the original integral. Now that can be done. So we do u times v, so we get x squared times 4 plus x squared to the 1/2 minus the integral of 2x times 4 plus x squared to the 1/2 dx. So then I'm going to leave this alone, x squared, 4 plus x squared to the 1/2. Now the second integral, the integral of 2x times 4 plus x squared to the 1/2 is also done via substitution. I'm just going to write it down. We're not going to go through that substitution, but we end up with 2/3 times 4 plus x squared to the 3/2. And again, all of this is being done from 1 to 0, or 0 to 1. So the second integration is done by u substitution as well. And when you plug them in, I get minus 5.217 minus negative 5.333. So we get something along the lines of 0.116. So that was a pretty messy problem, but you can see that these things can be very sneaky as well. Why don't we go ahead and check that one? I don't know if I've checked it before, but probably I have. What was the original integral? The original integral was from 0 to 1. And it was x cubed divided by square root of 4 plus x squared. So yeah, 0.116. So it came out correct. Anyhow, that was a very difficult problem. I don't anticipate seeing any that difficult on the homework. But yeah, why don't I go ahead and stop the recording.